Okay. So now we have time to start. The next speaker will be Sergey Shpectorov, University of Birmingham, and he will talk about solid subalgebras and algebras of Jordan type half. Welcome, Sergey.
Yeah, thank you very much for the invitation to speak. I should apologize for two things. First of all, I gave a very similar talk at a recent conference in Harlow. So if there are people in the audience who attended that conference, it will be quite similar to that talk. And secondly, my PhD student is currently having a viva. And so I may be interrupted any moment if they want to tell me the results. So there might be interruption during my lecture. Okay, so I will be talking about algebras of Jordan type half and about a special property of the subalgebras in this algebras. And I'll have to repeat quite a bit of what Tom already told you, but I think it might be even, I'll go through those parts quicker. But I think it might be good for you to sort of have a second look at some of the definitions. So, wait a second, my pointer is in the wrong place. So, so we start again with the fusion law. We just saw a similar table. This is the fusion law I will be mostly concerned with. Again, it's we have a set 1, 0, and a half in this case. That's my set F, and the map is into the set of subsets. The only difference with Tom is that I don't use the set brackets for the sets. I just list the elements in each set in the cell of the table. Again, the definition of the axis, we also just looked at it a minute ago. Again, slightly different notation. For Tom, we have the notation A lambda E. So E is a typical idempotent, a typical axis. For some reason, I use ABC for axis. So that will be slightly different. And also, I put the axis in round brackets. And so A lambda of A is the lambda eigenspace for the adjoint map of an idempotent A. We don't assume that this A lambda of A is non-trivial, so we don't assume that lambda is necessarily an eigenvalue. Lambda is just any scalar in the field. Okay, so the notation, if we have a bunch of possible values of lambda, we have a set capital lambda, and then a capital lambda of A is just the direct sum of the corresponding eigenspaces. And so we now have a fusion law, which is contained in our field of scalars. And we have an algebra A, which is commutative non-associative over the field F. And an F-axis is an idempotent such that, well, first of all, the adjoint of A is semi-simple, and all eigenvalues are in the fusion law F. So that is a very limiting property already, but even more so is the second property, that the fusion law actually tells us how the eigenvectors multiply. So if you multiply the eigenspace A lambda with eigenspace A mu, then all the products of eigenvectors lie inside the sum of eigenspaces A lambda star mu of A. So in particular, if lambda star mu is empty, then this right side, when lambda star mu is empty, the right side is simply the trivial subspace. So in this case, all products are simply zero, as Tom explained. Again, we always assume that 1 is an F, because A is an idempotent, and so the one eigenspace is non-trivial. And this means that 1 must be in the fusion law, because otherwise we cannot have property 1 satisfied. And we will essentially always assumes that our x's are primitive, and primitivity is slightly different from, say, the theory of Jordan algebras. And in our case, primitivity is simply the statement that the one eigenspace is one-dimensional spanned by the axis itself. Okay, an axial algebra is just an algebra A with a set of axes for a particular fusion law, and this axis must generate A as an algebra. And this is our notation for generation double angular brackets. We may assume that the fusion law is symmetric because the algebra is commutative, and because of primitivity, we can also assume that 1 star lambda is just lambda because a one eigenvector is just a multiple of the axis itself, and so you can immediately see that nothing else will appear apart from lambda eigenvectors again. And we can also assume that 1 star 0, if you have 0, that it can be taken to be the empty set. Right, so I showed you the fusion law, which I will be mostly concerned with. It is a special case of the more general fusion law, where we allow any number in place of a half, well, any number other than 1 or 0. And algebras of Jordan type are simply primitive axial algebras with such fusion laws. And this basically is, so here the fusion law and the property, the axial property is basically the axioms which define the class of axial algebras. So I will mention very briefly again that we have Matsuo algebras in this class, and they exist for all values of eta. We do assume that the field is of characteristic not equal to 2. And that is, of course, because we need to divide by 2. As you see in the definition, for 2, it doesn't work. Okay, so these are the algebras which are defined in terms of groups of 3 transpositions. I will not spend much time on this case, but they will pop up at some point later slightly. Okay, so this exists for all values of beta, and so this can be viewed as a generic examples of algebras of Jordan type. And of course, we must also have Jordan algebras, but they only appear for eta equal to a half. And the fact that they are algebras of Jordan type eta is expressed in this Peirce decomposition. It's a classical result about Jordan algebras. We should probably mention that not all Jordan algebras are axial, because you can have algebras without any idempotence, and we asked for the algebras to be generated by primitive idempotence. But all the simple algebras over fields which are algebraically closed, I think they are all axial algebras. Okay, so in fact, we don't have any further examples of algebras of Jordan type. So Matsuo and Jordan, that's all we have. And that is the current conjecture that we are trying to prove, that every algebra of Jordan type is either a Jordan algebra, or it is a Matsuo algebra, or a quotient of the Matsuo algebra. So Matsuo algebras tend to be simple, but they sometimes have some ideals infrequently, and so they may have quotients, and quotients of Matsuo algebras, they are algebras of Jordan type, but they are not Matsuo, so we need to add this as a special case. And quotients of Jordan algebras, they are Jordan algebras themselves, so we don't need to do the same for Jordan algebras. Okay, so I'd like to talk about what's known about the classification of algebras of Jordan type. Right, well, first of all, these two families are not entirely disjoint. In fact, they actually have an intersection. So some Matsuo algebras for n equal to 1/2, they are in fact Jordan. And the example, so there is a theorem actually due to Tom and due to Felix Rerin. from 2017, they determined all the Matsuo algebras which are Jordan, and these are the algebras for SN. And then there is an additional example for the group of order 18, as you can see here. And with one addition later by Yabe, who noticed that specifically when the statistic of the field is 3, then there are more examples. So this example sort of leads to a whole series of examples of Jordan algebras, but only in characteristic 3. Well, I should probably mention that if you, Sn is of course the while group for the type AN. So if you take any other simply laced while group, then that group is going to be a group of 3 transpositions. So there is a Matsuo algebra for it. And while for the other simply laced groups, the Matsuo algebra is not itself a Jordan algebra, but its quotient. So it would have an ideal, and the quotient over this ideal would be a Jordan algebra in this case. Right, and there is a recent result by Gorshkov, Mamontov, and Staroletov, who extended the result of Toms and Felix Revens and showed that this list is complete. There are no further Matsuo algebras whose quotients can be Jordan algebras. Okay, so this is again something that Tom already explained, this fusion law for algebras of Jordan type. It is graded, so it has an even part, which is marked with plus, and the odd part with a minus. And basically, if you look at the table, if it's split like that, you can see that even times odd is odd, and odd times odd is even, and so on. And because it is graded, we have an element of order 2, an involution, which corresponds to every axis. It acts as identity on the even part and as minus identity on the negative part. And so the grading of the fusion law results in the grading of the algebra, and so this leads to an automorphism of the algebra. Okay, and the Miyamoto group is just the group that is generated by all such Miyamoto involutions. Right, so what kind of group do we get? Is it a finite group or an infinite group? So here is a recent result. So let's suppose we have an axial algebra, and it doesn't have to be primitive, but it doesn't matter. But let's suppose that 1/2 is not one of the numbers in the fusion law. Well, then the automorphism group is necessarily finite. Okay, and here is a sketch of the proof. The automorphism group of any finite dimensional axial algebra is an affine algebraic group. And so if it has dimension 0, it is finite. So if it's not finite, it must have a positive dimension. Then its Lie algebra has a positive dimension, and this Lie algebra acts by differentiations. But if you take a differentiation of the algebra and you take an axis, then this little calculation shows that the image of A under the derivation is a 1/2 eigenvector. Okay, so if you don't have 1/2, you cannot have any 1/2 eigenvectors. So D of A is 0, and then it is a very brief argument to show that since D sends every axis to 0, and since axes generate the algebra, then D is trivial on the entire algebra. And so you cannot have any differentiations. And so this shows finiteness unless you have 1/2 inside the fusion law. So, we already mentioned that 1/2 was special because you had the examples of Jordan algebras when eta is 1/2. So now it is special in a different sense. So if eta is not a half, then the groups are necessarily finite. If eta is a half, the groups can be infinite. And we know that those cases which are Jordan algebras, they typically have the groups of automorphisms are the classical groups, typically, and they are definitely infinite when the field is infinite. So it sort of fits. It all fits into a very nice picture where 1/2 is a very special number. Also, 1/2 is special in some other senses, but I will not go into that. So the chair of the session also wrote a paper about why 1/2 is special, and he may have some comments about it. Right. So now I will try to review what's known about the proof of the conjecture that we mentioned. Well, first of all, in the initial paper where the class was introduced, we classified the algebras which are generated by 2 x's. Okay, so they are strictly of dimension no more than 3 with a very simple multiplication table. X, Y are the 2 x's, and S is a special element that's defined in terms of the product. It's actually xy minus eta x minus eta y. You can see it from here. So X, Y, and S always provide a spanning set. And so the theorem is that if A is any algebra of Jordan type eta, which is generated by 2 x's, A and B, primitive, let's define the scalar phi as such a scalar, so that the projection of B onto the one space A is exactly phi times A. This space, this is the one eigenspace. So we have the projection map, ignoring all the other components of the vector for other eigen values. And so the projection should be exactly phi A. Then for this value of phi, you have the algebra above, J of phi, and there is a unique surjective homomorphism from J of phi onto A, sending X and Y to A and B respectively. And furthermore, so eta equal to 1/2, as we say, is special. So if eta is not 1/2, then in fact the value phi is basically a 0, in which case we just have this algebra of dimension 2, just the field plus itself, a very simple algebra. So in this case, AB multiplied to 0, or phi can be eta over 2, and there is a 3-dimensional algebra 3C of eta with a very simple multiplication table that exists in this case. And in this case, this algebra has 3 x's, and the group that acts on it is a group of order 6 S3. Okay, so if eta is not a half, only this exists. If eta is a half, it is sort of implicit here. Any value of eta gives rise to a good algebra. So that's why eta is 1/2 is much more difficult, because there is this infinite family of algebras which are generated, which exist only for eta equal to 1/2. Okay, what are the consequences of this? In the same paper, with some correction later, if eta is not a half, then every algebra of Jordan type eta is in fact isomorphic to a Matsuo algebra or a factor. And so in this case, the conjecture is proven. That's exactly the claim of the conjecture. So with all these values of eta out of the way, let's now assume that we focus on eta equal to exactly 1/2. We will mention that in another paper, it was shown that every algebra of Jordan type admits a unique bilinear form. We call it a Frobenius form, such that it associates with the algebra product. This is expressed by this equality. And it is sort of normalized so that every axis has length 1 with respect to this form. So in particular, the form is non-zero. It always exists. It is always unique for any algebra of Jordan type 1. It's not part of the axiomatics. It just follows from the fusion law. Okay. So there is another way to look at the classification of algebras of Jordan type half. So if eta equal to a half, all this infinite family of examples for all values of the parameter phi, they are all in fact Jordan algebras. In fact, they are all spin factors. And here on this page, I briefly remind you what the spin factors are. They come from the Clifford algebra construction, but here I'm just giving the direct multiplication. So let's have a vector space V over the field F. And let's suppose that you have a form Q on this, and B is the associated symmetric bilinear form. Then the spin factor SVQ is the algebra defined on F plus V. So every vector is a pair, a scalar, and a vector from V. And multiplication is given by the formula here. So alpha plus U times beta plus V is this expression in terms of the bilinear symmetric form that's associated with Q. It's very easy to list what the eigenvectors, idempotents are, and then if you have a basis of elements of norm 1 in V, then this spin factor is an axial algebra. And here is a theorem that tells us that if V is of dimension 2 with a basis AB, so that Q of A is 1 and Q of B is 1, and B of AB is Xi, so Xi is a parameter. Then this algebra is typically generated by those two idempotents A and B, with one exception when Xi is 1. And exactly the same exception sort of eliminates one more difficult case, but in all other cases, this algebra AB is in fact isomorphic to our algebra J of phi, I mean the one which we discussed here. This one, yeah. And there is a simple relation between the parameter phi and the parameter Xi from this picture. Okay, so there is, I mean, if Xi is 1, there is also an algebra, but simply it will not be the spin factor in that case. But almost always it is a spin factor. Right. I don't think I'll have time to actually use this information later, but for our later proof, it's very important that this spin factor, it has a different nice basis. So if Xi is not equal plus minus 1, which will pop up later as a condition, so we have, because Xi is not 1, in particular, this S of Xi is the same as our J of phi. And furthermore, it is simple of dimension 3, and the form on it is non-degenerate, as we will discuss later. And under these assumptions, when Xi is not plus minus 1, this algebra S Xi contains exactly two nilpotent 1 spaces spanned by U and V, and we have a different basis U1 and V, and we typically scale U and V so that UV is an 8th, and that's the basis, you know, we actually work. Although I'll probably won't have time to show you the detail how it all works. Right. Okay, another relevant fact that I need to mention is that, well, of course, if you have an axis and you have an automorphism, if you look at the definition of the axis, you know, if you apply an automorphism to an axis, you again have an axis. So you can start from your initial set of 2 or 3 x's and small set of x's initial, and then apply automorphism groups and get a lot more x's. And when you apply all automorphism from the Miyamoto group, you get something that we call the closure of the initial set. And this is also a set of generators, and the Miyamoto group now acts on this set, and this leads to a concept of an X set and to some things which we had to do when we try to compute these algebras, sort of the computational side of the theory. So, so this is a nice set of generators, and in particular, what can be proven, and this was proven in a paper with John Hall and Yoav Segev in 2018, that every algebra of Jordan type is one closed, that is, it is spanned by x's. You don't need even any products, already x's, as long as a set of x's is closed, then the set of x's already spans A. Okay, so we discussed the case of two generated algebras in detail. There is a similar result from 2020 by Gorshkov and Staroletov. They classified all algebras which are three generated algebras of Jordan type half. So I mean, every algebra, you have a similar description in terms of some universal construction. So there is an algebra of dimension 9, J alpha, beta, gamma, psi. Alpha, beta, gamma, psi are four independent parameters. And I mean, it has very explicit products in terms of these four parameters, so that every algebra of Jordan type half, which is regenerated, admits a homomorphism from J onto A, which is surjective and sends X, Y, Z to A, B, C respectively. And of course, alpha, beta, gamma, and psi have to be chosen carefully. They're just values of the Frobenius form as explained on this page. So basically, this is the universal algebra. I mean, it can be defined over the ring of polynomials and alpha, beta, gamma of deltas, and it would be slightly more difficult to explain this homomorphism. But so I think it's clear that we have sort of an object which is universal and it describes all possible algebras. It's typically, I mean, sort of, if you take alpha, beta, gamma, psi arbitrarily, sort of generically, then the algebra is actually a simple algebra. And if the field is algebraically closed, it will be the 3x3 matrix Jordan algebra. So they are all Jordan algebras, these examples for three generators. And but for some values of alpha, beta, gamma, psi, it's not simple. It has quotients, and in some cases it's not a matrix algebra. It's slightly different. But sort of generically for random values of the parameters, it is a matrix algebra. Right, we will need some properties of this algebra. So let us take two of the three generators, say X and Y. So we have the Miyamoto involution tau X, we have the Miyamoto involution tau Y. Let's call the product of these two rho. Then this rho, if you check how tau X, tau Y defined, tau X and tau Y always preserve every algebra they are contained, X and Y are contained in. And therefore, this rho also preserve the subalgebra X and Y generate. So this XY is that three-dimensional algebra that we discussed. Okay, it was in terms of phi. Now phi is called alpha. Okay, so phi and alpha is the same. So rho preserves this U of dimension 3, and it also acts on the complement. So we will make a restriction. We will ask for this parameter alpha or phi or whatever not to be in some small set, and as a consequence of it, it will be that U will be simple of dimension 3, and this will imply that we basically can decompose the entire algebra into U and its complement, U perp, and this row will act on the algebra and its complement, and that's how we will look at it. I think I got ahead of myself. I haven't restricted the values of alpha yet. So this is not always true, unfortunately, but it will be true for, under some minor restrictions. Well, anyway, so we can check a few properties of the action of rho on the algebra in GAP, because everything is very explicit. And in particular, the minimal polynomial of rho in the action on U is below this. It's given by this polynomial R of t. It has 3 roots, 1 and 2 further roots. And the action on W is given by another polynomial. Again, 1 is an eigenvalue, and there are 2 more from a different polynomial. There is some relation between the roots of these 2 polynomials, P and R. So if the roots of P of t are 1, zeta, and zeta inverse, now the product is 1 of the 2 roots, right? So it's zeta and zeta inverse. Then the roots of this polynomial are 1, zeta squared, and zeta to the power minus 2. Okay. Also some facts about the dimensions of the eigenspaces. Right, so I'll go really quickly over this. Tom just spent a whole hour explaining how to get this result. This was a real breakthrough because nobody knew how to do the 4-generated case. It's much more complicated, but now it seems sort of we have this breakthrough, and perhaps we can go further, because this is really important case, because this is the number of generators where the 2 families, Matsuo and Jordan algebra, when they separate. So there is a 4-generated Matsuo algebra that's not Jordan. So here the 2 families branch. And well, the only thing I should say is that while they established the exact upper bound of 81, there is no explicit description of the same kind that we had for 2 generators and 3 generators. That would be very desirable to obtain, and that's my question here, whether it is possible to get a similar description for sort of universal algebra, at least for eta equal to 1/2. And I should say that one of my PhD students works on this question on a particular case when the algebra is baric, has a very large ideal. Right, finally, I arrive at the main topic of my talk, solid subalgebras. This is a joint project with Ilya Gorshkov and Alexey Staroletov from Novosibirsk. Sort of we had the first ideas already quite long ago, and this was discussed a couple of years ago at a workshop in Birmingham. But we try to generalize this to the best possible result, and I think we finally have it. So hopefully it will be finished, the draft will be finished in a few weeks. But at the moment, it's still sort of a paper in preparation. So what is this about? So let's suppose we have an algebra of Jordan type half called A, and we have axes A and B. Then we look at the subalgebra that A and B generate. So this is a small algebra of dimension no more than 3. And we call it solid if and only if every primitive idempotent in U, okay, it is a primitive axis in the entire big unknown algebra A. Okay, so
And how you understand the primitive idempotent? What is it in algebra?
Primitive means the same as I already said. The one eigenspace is one-dimensional for A. So basically, this requires to prove that outside of U there is no one eigenvectors for for the idempotence in A, apart from, so you see inside U, you have 0 and you have the identity of U. Yeah. Those are not primitive in U, and therefore I'm not saying anything about them. I'm only saying about the idempotents which are already primitive in U. Okay. So 0 is excluded, identity of U is excluded, but all the other idempotents, they are primitive in U, and they must be shown to be primitive X's in the big algebra A. And the trouble is, of course, that A, nobody knows what A is. Yeah. So A can be big or small, it can be known or unknown, arbitrary of Jordan type, half. Okay. So it's a pretty sort of tall requirement. Then some idempotents must be primitive X's in this unknown algebra A. But the surprising result is that typically all the two generated subalgebras are solid. So typically we have a lot more eigens, a lot more X's than we expect. Okay, and here is the main theorem. Suppose that A is an algebra of Jordan type half for X's AB in A. If AB, if the value of the form, so which appeared as phi, which appeared as alpha later. So if this value A comma B, the value of the Frobenius form, is not in the set 0, 1, 1/4, then the subalgebra they generate is definitely solid. Okay, so you have plenty more X's in the big algebra. Okay. Right. A simple example of this is when A times B is 0. In this case, U is just two-dimensional, algebra 2B, and AB are the only X's in U, and then of course it is obviously solid. But of course, this is not the interesting case. Typically, U is three-dimensional, and it has, if the field is infinite, then it has infinitely many idempotents, and all of them are going to be X's. Okay? So that is the theorem in preparation. Okay, well, first of all, if you look at the statement, we can extend the field and it's going to be all the same. So we might as well assume that F is algebraically closed. And then secondly, because the value of phi AB is not in 0, 1, the algebra U is three-dimensional and simple. So we will assume that phi is not in 0, 1. So U is three-dimensional and simple. It means also that the Frobenius form on U, which you, I mean, if you restrict from A to U, you will get the same form as U normally has, because the form is always unique. So the form on U, it is the same as restriction from the form of A to U. So this form is going to be non-degenerate, so U has no radical in this case, and therefore the entire algebra A decomposes as a direct sum of U and U perp. And furthermore, this U perp, which we call W, this U perp is going to be a module for U. It's very easy, I don't mention it here, but you can easily see that U times U perp is contained in U perp. So U perp is a module for U, which is important for our proof. And furthermore, this W is sort of isomorphic AU, and we can do the calculations, and that's how I already mentioned the calculations and the polynomials. These two polynomials, P and R, that's exactly the minimal polynomials of rho, tau A, tau B in the action on U and the action on W. Okay, and so we have eigenvalues of U acting. So those polynomials, they were in the action on just the 9-dimensional algebra, but it's an easy argument using the fact that A is 1 closed, that you'd have exactly the same minimal polynomials on any unknown algebra A. So it is indeed the same polynomials P and R that you encounter here. Right, so we just have 5 eigenvalues in the action of rho on the big algebra A. They are 1, zeta, zeta inverse, and then also we have zeta squared and zeta to the power minus 2. Furthermore, because the minimal polynomial is easily shown to be without multiple roots, we have the following decomposition of the entire algebra A as a direct sum of 5 terms. Okay, and then the whole point is to show that this grading is not just, like we have a grading with 5 terms. So we will show that this grading is a Z grading with, so this is the zeros term, this is the minus 1 terms, first term, second term, minus second term, and all other terms just trivial. Okay, so we will show that this is a Z grading. Okay, and this is achieved via some calculations, and I don't think I have time to show that, but this is where we use that action in terms of a different basis. If you remember, we had a basis with UV, 2 nilpotent one spaces, and identity in U. So in checking that this is true, we use some calculations involving that basis. It is much more convenient here. Okay, but once we establish that this 5-term decomposition is a Z gradient, it immediately now follows that if you take any lambda in F and you act on the i's part of the gradient with a scalar lambda to the I, then this is going to be an automorphism of A for every lambda. So you have an infinite group of automorphisms, and this infinite group of automorphisms, it acts transitively on the primitive idempotence of U. And so since we have 2 of them X's, so all of them have to be X's. And this finishes the proof of the theorem. Well, actually, this proof would be very, very, very simple if we eliminated not only 0, 1, and 1/4, but also if we eliminated a couple of other values which lead to orders of rho equal to 4 and 5. So starting from what I think 7, the proof is just a page long. It's very elementary. But in order to include the small values, the small orders of rho, and to achieve the best possible, so that requires quite a bit of calculation to include all the possible values. Right, anyway, so the value of 1/4 is exceptional. So so not only 0 and 1 are removed, but 1/4, this is the case where 3c of 1/2 arises, and this is an exceptional situation. In this case, we cannot show that we do have extra idempotence in the algebra, but we cannot show that they are excess. So this is a finite situation that remains finite. Right. So now suppose we have the theorem. So what's next? Right. So what do we do with these 3 exceptional values? Well, by the way, this theorem applies to all characteristics except the characteristic 2. So there is no restriction on F here, apart from the usual one. But the next result is specific for characteristic 0. And it uses the same tricks as that proof of finiteness of the automorphism group. So here is the second theorem. Suppose additionally that F is of characteristic 0, and then the exceptional algebras arising for the values 0 and 1. So J of 0, J of 1, and there is a quotient J1 bar of dimension 2. So all these things are solid, and in these 3 cases, we have infinitely many idempotents, but they form a variety of dimension 2. In one case, it is a single component variety. In the other case, there are two components, but both components, all of them have dimension 1. And basically, we prove this by showing that every component of this variety of idempotents has infinitely many points, which means that the variety of idempotents, which can be shown to be indeed an algebraic variety, it must have dimension, positive dimension. So then it has dimension 1, and then it has to be the variety of all idempotents because it also has dimension 1. So this basically uses a bit of algebraic geometry in the argument, and it uses the dimension of the variety to establish the equality between the set of x's and the set of idempotents. Right, I think I am running out of time. So this is the end of this argument. And so to conclude, in characteristic 0, the only possible non-solid U is the algebra J of 1/4. When it contains exactly 3 x's, 3 primitive x's. Okay, it has more idempotents. It has infinitely many idempotents if the field is algebraically closed, or if but only 3 of them are x's. So that is the only possibility that's not solid. Right. And so we have the following nice corollary. So suppose that F is algebraically closed and characteristic is 0, and A is algebra of Jordan type half over F, then either A contains an infinite solid line, and so it has an infinite automorphism group, or A is a Matsuo algebra or a factor of a Matsuo algebra. So we see a clear branching. So Matsuo algebra, which are basically arise as the only possibility for the finite automorphism group. Okay, so everything else has infinite automorphism group, and so we can basically focus on the case when we have solid lines and only assume that we always have this. Right. The question, of course, can this be generalized to the fields of positive characteristics? The trouble is that we use the fact that we have infinitely many x's. So xset in this case is infinite in characteristic 0, but unfortunately it folds in positive characteristic into a set of size p. So this argument falls apart. So the known set of x's is finite in positive characteristic, and that's why this argument cannot be applied. But maybe there is another way to argue, and I hope somebody will find a way to generalize this to positive characteristic. Right, and the final slide. So what I'm thinking now is that we can actually switch now to the language of geometry and try to classify these things in terms of geometry. So we can view the primitive x's as points, and the lines would be the two generated subalgebras. And this means we would have several types of such lines. So there would be orthogonal pairs, that's algebra 2b. So just pairs A, B such that A times B is 0. We would have toric triples. So this is the exceptional non-solid J 1/4. Okay, also finite lines. And then we have infinite lines. We have the flat baric lines J of 1 and J of 1 bar. And we have toric lines. Basically, baric lines, they are copies of the field with the additive structure. And toric lines, they are copies of the multiplicative group of the field with a multiplicative structure. So they are basically like tori in the algebraic group that we get. And sort of the first kind is the additive torus, and the second one is a multiplicative torus. Right, and if we want to use this geometry, we probably need to know how lines can actually what kind of planes we can have. And that comes from the algebras, subalgebras of which are 3 generated and which are 4 generated. And that's sort of, once we understand 3 and 4 generated, maybe we can develop sort of a geometry point of view for this, and maybe it will help to classify them. Okay, I think that is the end of my, no, there is one more slide. So just to mention that, Ilya and Alexei found an example of a Matsuo algebra, which is not a Jordan algebra, but it does have solid lines, and it arises for 3 covers of the symmetric groups. And so here, the group has 2 orbits on the lines of the Fisher space, and the geometry that underlines the Matsuo algebra, and sort of they can be classified into the vertical lines and horizontal lines. And the vertical lines in this case are all solid, and the horizontal lines are all non-solid. And so this is an example where the full automorphism group is going to be the normalizer of the Cartan subgroup in the suitable algebraic group. Okay, and a bunch of open questions. Some of them are already actually answered since I first made the slide. So here is one question, is it possible to generalize the example from S4 to any Sn? And how about 3 to the n Weil groups for simply laced? And this question was already answered by Yari Desmet, who I think is somewhere here in the audience. And he answered yes and yes. This all can be generalized to this example. So we have solid lines for all these algebras, for all these non-Jordan algebras. Can all Matsuo algebras and quotients which contain solid lines be classified? Again, Yari says he can do it, but I don't know if the result has been already written sufficiently, or whether it is all definite. And can all Matsuo algebras with infinite automorphism groups can be classified? Most likely the answer is exactly the same as the second question, but it's not clear per se. And finally, can all Matsuo algebras be classified where automorphism of the Matsuo algebra is larger than the initial group of 3 transpositions? And for eta equal to 1/2, it's one question, and it's entirely different question for eta not equal to 1/2, but the examples actually exist when that full automorphism group is larger, which was very surprising. There exist 3 families of examples where the algebra is actually larger, and there are some unexpected new axes in the algebra. And this is the PhD project of a PhD student of mine, Fari Al-Harbi. The line didn't quite fit into the slide. Okay, thank you for listening. That's all I want to tell you.
Yeah, many thanks, Sergey. So let us thank you for your interesting, great talk, as we already seen in comments. You already asked some questions by yourself, so maybe it's okay. We have time for other questions, comments. Welcome.
Sergey, what are the examples on the last slide that you were referring to, the unexpected examples?
You mean here for the Fari, yeah?
Yes, that's right.
Okay, just a moment. So there are 3 series. First of all, Sn inside Sn plus 1 for a specific value of eta, the parameter eta. The algebra of the Matsuo algebra for Sn plus 1 has a radical, and the quotient over the radical is exactly the Matsuo algebra for Sn. And so basically all the x's for Sn plus 1 map into the Matsuo algebra for Sn, and the full automorphism group for Sn for that particular value of eta will be Sn plus 1 instead of Sn. So bigger, yeah? And there are 2 similar examples. O to n plus of 2 inside SP to n 2 and O to n minus inside SP to n2, again, for specific values of eta, we have the same situation. The larger example, the Matsuo algebra for SP to n2, for that particular value of eta has a radical, and the suitable orthogonal group gives the basis of the quotient. Okay, and so inside, yeah.
So in this question, you're really asking for a finite but substantially larger than G. Is that the question?
Yes, it is finite in this case. But you see, if you have a Matsuo algebra with eta not equal to a half, then the algebra is finite. Then the automorphism group is finite by that theorem, you see, because there is no
right.
Yeah. I mean, it got to be finite, yeah?
Yeah, okay, yeah.
But it is not as expected. It is not the group of Satan's positions that you expect.
Okay, yeah, interesting. Yeah, thanks.
Thank you. Other questions? Or yeah.
Yeah, Sergey, maybe as a small remark. So when I said that I can classify all Matsuo algebras containing solid lines, it is not with quotients.
I remember. So I asked the question for Matsuo algebras and quotients, and you told me that he knows how to classify at least Matsuo algebras, which contain.
And if my newest calculations are correct, then they intend to be, well, they are the same for the answer to the second and the third question is the same.
Yeah.
And the only issue with the quotients of Matsuo algebra is like the intermediate quotients of this four-generated example that was like the derived subgroup of a special unitary group over the field of two elements, which appeared in Tom's talk.
Yes, indeed.
Yeah, but it should be feasible, I think, to do it. But I haven't had time yet.
Yeah. Well, I mean, if you look at the claims right here, that's quite a lot. Yeah, I think the Viber is over, by the way. And I mean, anybody has any questions? Or I need to go to my PhD student because he's knocking at the door.
Thank you again, Sergey.
Okay, thank you very much.
We have some few, actually a couple of minutes to the next talk. Okay.